Hi, everybody. I'm going to talk a little bit about the orbitals going on in these SN2 and E2 reactions. This is mostly for those of you who are curious as to why we're doing things the way we are. So if we have just a normal SN2 reaction here, so I've got sodium cyanide, I've got a secondary alkyl bromide. So at this point, what we can do is we know that the cyanide comes and attacks that carbon, the bromine leaves, and then we get inversion of stereochemistry here. Okay, and so when we attack with our cyanide, that's going to come from the front because the bromine is pointing to the back, and that's going to push our H to the back. Okay, so if we're kind of wondering, like, why does it do that? Why does the nucleophile have to come from the opposite side of the leaving group? A little bit of it can be explained from the transition state here. So we see that as we have the bromine, right, this bond is breaking while this bond is forming. Because those things are happening at the same time, having them on opposite sides does just kind of make sense in terms of keeping your electron density spread out, making sure that you don't have atoms running into each other. So you can kind of pick that up from the transition state that we want to have these two things on opposite sides, right? But there's also an orbital reason that we want to be coming from the opposite side of the leaving group, okay? That all comes down to orbitals, okay? The antibonding orbital is actually what we're forming our bond to, okay? Because as we break the carbon-bromine bond, that is an interaction of our antibonding orbital from our carbon-bromine. Okay, so in green here is shown the sigma star of my carbon-bromine, okay? So if we look really carefully here, we want to note that the bromine has a p orbital that it's using, the carbon is going to have an sp3 orbital that it's using, and for the bond, you would have overlap between the two atoms, right? That would be our filled orbital that has 2 electrons in it forming that bond. But for every bonding orbital, there's an antibonding orbital as well, okay? And it's these antibonding orbitals that when we put electron density into them, then we break the bond, okay? So right now what we have is we've got a bonding orbital of carbon-bromine, which currently has 2 electrons. And then up here somewhere is our sigma star, which is empty, okay? As soon as we populate this, we're going to break the carbon-bromine bond. Okay, and then we can actually form a new bond from the antibonding orbitals. So the thing that's breaking the bond is going to be our nucleophile, okay? So our nucleophile is going to come in. We've got a lone pair here in an sp orbital. Let's shade that a little bit in. Okay, so we have our lone pair in an sp orbital. So as this comes in and overlaps with that antibonding orbital, and we put those 2 electrons into the antibonding orbital, oops, that's going to break that carbon-bromine bond, and then we're going to form a new carbon-carbon bond with this orbital and the sp orbital, okay? So as the nucleophile comes in, the carbon to bromine bond breaks, and the carbon-carbon bond forms. Okay, so as we do this, then we're getting that formed together, Okay, so that's why the SN2 happens the way it does, because we have to, the antibonding orbital is what we have to line up with. And if my bromine is pointing that way, my antibonding orbital is going to be majorly on the opposite side of that bond. Okay, completely straight from it. So if you're looking at a model, okay, so this is the model of it. And I did kind of a weird bond rotation to get here. So I had this for my view, not for a mirrored view. Okay, so this is what we are working with originally. The bromine is in the back. Yep. Okay, so bromine is in the back here. So what we're working with is, if I can identify this carbon-bromine bond, which is right here, my antibonding orbital is going to be mostly right here, as well as right here. Okay, so since we want to make a bond with the carbon, we want to focus on the carbon's portion of the antibonding orbital. So we're going to attack right here, and then the bromine is going to pop off that way. Okay, so that's how the SN2 reaction works, and why you have to have opposite side attack of your leaving group, because you're accessing that antibonding orbital, which sits right here. All right, so let's look at what's going on with the E2 reactions. Okay, so for E2, the real question is, why do we care about antiperiplanar? Because it seems very arbitrary, and then I'm just making stuff up. But there is legitimate orbital reasons for why we are doing it the way we're doing it. So the main thing is, we want to think about, I first just want to remind us what a pi bond looks like, and keep in mind that's what we're making in an E2 reaction. So a pi bond is an overlap of two p orbitals here and here. Okay, so that's actually, let me change that to green real quick, just so we're consistent. That's what we're looking for in a pi bond made of p orbitals. That's what we're looking for. Okay, two p orbitals overlapping, we form good overlap on the top and the bottom, and we have our pi bond. Okay, so we know that we need to have antiperiplanar for E2, but what we're not sure about yet is the why. So I'm just going to draw in the bond here. So I'm going to draw in the bonding orbitals for my CH bond. So I've got the H just has an s orbital. The carbon is going to have an sp3. So I've got my sigma bond of the CH, okay, is an S and an sp3. My base is going to be whatever's holding that lone pair. Okay, so we got something like that. So that's my base, and that's my CH bond. So what's going on with the bromine side? I should have changed colors here, but that's okay. So again, we're looking for the antibonding orbital of the carbon bromine, because that's what we want to populate and break the carbon bromine bond. Okay, so on this side over here, we're going to have our antibonding orbital. Do that a little too big. Okay, again, we're finding the carbon bromine bond, and then straight from either side is where our antibonding orbitals are going to sit. Okay, so then we have that for our sigma star of our carbon bromine. Okay, so if we look to see what's happening here, as this base moves in to grab the H, this electron density in that sp3 bond is going to get shared across to the antibonding orbital and then break that carbon bromine bond. Okay, so basically what's going to happen is you're going to see a rehybridization of these two orbitals to go from the sp3 to a p orbital. to form that pi bond. Okay, the carbon-bromine sigma bond will be broken in that. Okay, so as we add electron density to that antibonding orbital, that bond's broken, bromine is going to be released, and then we end up with our new pi bond. Okay, so we're going to get to this. Okay, new pi bond. Okay, so that's kind of what's going on in the orbitals. Some people find it very, very helpful. Some people find it confusing. I'm not really going to be testing you on this so much as just making sure that the people who do want to know about this know what's going on with the orbital circumstances. So as always, let me know if you have any questions, and I will see y'all later.